So these are the questions from lesson 2 and lesson 3. The first question I want to solve is, given the following data, determine the gravitational potential energy of, as soon as it says gravitational potential energy, I think of this formula, minus G m1 m2 over r. It says the gravitational potential energy of the moon within the Earth's gravitational field. So obviously m1 and m2 is going to be the mass of the Earth and the mass of the moon. Your G is given in your physics data sheet, 6.67 times 10 to the minus 11 newtons meter squared per kilometer squared. And your radius is going to be your Earth-Moon distance. This is the distance between the two centers. So from the center of the Earth to the center of the Moon. If it gave us the distance between the surfaces, it'll also have to give us the distance, well, the radius of each. So all we have to do is plug and play. So for A, we're just going to plug in the mass of the Moon, mass of the Earth, divided by the Earth-Moon distance. We're going to get our result. And for B, the Earth within the Sun's gravitational field, same thing, the Earth and the Sun, and the Earth-Sun distance. I don't have a calculator, so I'm not going to be able to solve it. I'm not going to be able to answer it. 2003 Hsc paper. A satellite of mass 150, I'll use this, 150 kilograms is launched from Earth's surface. So from the surface, what do we know? We know that acceleration is 9.8 meters per second squared into a uniform circular orbit of radius that. Now it tells you the radius of the orbit, so that includes the radius of the Earth, because the radius of the orbit goes around the Earth. If the radius of the orbit started from the surface, that'll give you a weird path like that. So the radius of the orbit includes the radius of the Earth in order to get a proper orbit like that. Calculate the magnitude of the gravitational potential energy of the satellite. Very simple. EP equals minus G m1 m2 was given up here. M2 straight from the physics data sheet. 6 times 10 to the 24 kilograms, SI units. So 150 times 6 times 10 to the 24 kilograms, all over 7.5 times 10 to the 6 meters. And you should get a result. 2008 Hsc paper. The graph below represents the gravitational potential energy of a mass as it is raised above Earth's surface. So the height above Earth's surface, so it starts from the Earth's surface. From the graph, what is the gravitational potential energy of the mass when it is 1 Earth radius above Earth's surface? This is tricky because it says height above Earth's surface. So at the Earth's surface, it's going to be equal to that. 1 Earth's radius above the Earth's surface is going to be equal to that. So your answer should be this value here, which is going to be minus 0.8 times 10 to the 8 joules. Now I know in class I think I got confused because I thought this was starting from the center of the Earth, but it starts from the surface of the Earth. Let's go down a bit. Next question. International Space Station launch pad to space. So the International Space Station over here is launched into space. It weighs 150 tons, that's your mass. It's positioned 380 kilometers from the surface of the Earth. And it's just saying find the GPE, the gravitational potential energy. Now you're given your G, you're given your M1, which is 150 tons, which is 150,000 kilograms. You're given your M2, which is the mass of the Earth. And the thing is, in the physics data sheet, they don't tell you the radius of the Earth. So I just got this value here. But if they're going to ask a question like this in HSC, they would obviously need to tell you the radius of the Earth. So you can add the radius of the Earth to the altitude of the satellite and you can get your total distance, which is what you're going to plug into here. So this question should have had the radius of the Earth embedded in the question, and it probably did, because as you can see, there is, like, it starts straight away. It probably gave you that before the question started. Anyway, that's how you find the gravitational potential energy. B asks how much work needs to be done to increase its orbital radius by 20 kilograms. Now, work done was just force times displacement. So displacement is 20 kilometers, which is 20,000 meters. Always remember SI units. We can find the force from here, 1m2 over r squared. We know that the gravitational potential energy is equal to the work done. So if we find the change in the gravitational potential energy, we'll find the amount of work done. So if we put in the new radius, we're going to get a new gravitational potential energy value. The difference between them should be the work done. Moving along, 2009 Hsc paper. A satellite is moved from a geostationary orbit to a higher orbit. Higher means higher gravitational potential energy. Which statement about the orbit change is correct? During the move of the gravitational potential energy decreases? No. Energy increases. Energy stays the same. Gravitational potential energy increases, and kinetic energy decreases. So as Ke decreases, gravitational potential energy increases, but the energy stays the same always. Energy always stays the same. The change in gravitational potential energy is independent of the mass. No, it's not independent of the mass, because in the formula you've got m1 m2 over r. The work done is the difference between the gravitational potential energy of the higher orbit and that of the geostationary orbit. That seems correct. The work done is the energy required to move the satellite, which is in the gravitational field, from a very large distance. No, that's the gravitational potential energy. C is your answer. 2006 Hsc paper. Question 18. An object is stationary in space and located at a distance 10,000 kilometers from the center of a certain planet. So that's your R. It is found that 1 megajoule of work needs to be done to move the object to a stationary point 20,000 kilometers from the center of the Earth. So your change in gravitational potential energy is 1 megajoule. Calculate how much more work needs to be done to move the object to a stationary point 80,000 kilometers from the center of the Earth. Doesn't seem too hard, does it? EP equals minus G m1 m2 over R. Now it tells you 2R minus, or I should say, this equals, let me put it this way, change in gravitational potential energy equals this minus this, because 20,000 kilometers and 10,000 kilometers, it's just double the radius, and that equals 1 megajoule. So now that we know that, it's very simple to just say minus 2. It's kind of like saying minus 2 plus 1. It's just going to equal to minus G m1 m2 over R equals 1 megajoule. So we've got that. So we know that the gravitational potential energy at 10,000 kilometers is equal to 1 megajoule. Calculate how much more work needs to be done to move the object to a stationary. I'm assuming 80,000, because 80,000 is 8 times this. So if we're going to multiply this by 8, then we're probably going to need to multiply this by 8. That's how I would solve it.